and thank you for coming this afternoon, very rainy, snowy afternoon. And it's my great pleasure to share with you our recent data on developments for new possibilities of transmission electron microscopy for analysis of nanomaterial properties. This is a very new approach with respect to conventional TM. This slide shows my group in Tsukuba. I'm living in Japan for the last 20 years, and the group is pretty large, even compared to average group in Japan, so something like 20-25 people, depending on the year. And the main power of our group is basically Chinese postdocs and Chinese researchers. On this slide, I think 2/3 of them are from China. And we international group, we have Indian people, Iranian people, and of course Japanese. There are 4 Japanese people here on this slide. And because the group is so large, we can spread over a variety of different topics. And the trademark of our group that we do everything in-house. So we synthesize our materials by ourselves. We analyze these materials by using different microscopy techniques and Raman, XR, FTR, cathode-luminescence, photoluminescence. And because historically we are transmission electron microscopy group, of course we have a lot of TM activities. We have 4 high-resolution electron microscopes in my group, 200 keV, 300 keV. And we try to utilize in situ TM, just this novel technique to get access to the mechanical, electrical, thermal, and optical properties of materials. And lastly, we try to prepare different prototypes of functional devices, because you know that Japan suffers from energy problems these days, and we try to make different energy-related devices, something like lithium batteries, nanorheostats, conducting circuits, transistors, light sensors, gas sensors, and solar cells. And we try to get some funding from different Japanese companies and to entertain these companies to use our developments. I prepared this periodic table just to give you some flavor of the chemistry of materials we are studying at NIMS. And the color code is like this. We analyze borides, carbides, nitrides, oxides, sulfides, phosphates, and selenides. And the color code is, if you look, for example, at zinc, we prepare zinc sulfide, zinc selenide, zinc oxide, and zinc phosphate at different morphologies. These morphologies are shown here. It could be different nanotubes, nanobelts, tetrapods, mesoporous materials, nanoparticles, and heterojunctions, whatever you can imagine in a nanoscale world. And for all this bunch of studies, 2 years ago, we were selected for Thomson Reuters award, which is called Research Front. It means that Thomson Reuters realized that these studies can make a new contribution to the science of 21st century. And this picture is just normal high-resolution transmission electron microscope, which we use in our studies. And this is called objective lens aperture. It's located here, and people call this aperture the heart of the microscope, because everything depends on the quality of this lens. And this objective lens ball piece has 2 parts, upper and lower, where people usually introduce TM holder. This gap is rather small, just 4 millimeters. And for many years, since discovery of the microscopy back in 50s of 20th century, people use a microscope as an enhanced eye, human eye. Because these days we can zoom in the structures up to 2.5 million times. You can see individual atoms, individual vacancies, and so on. But my idea was to try to find new possibilities of TM and to merge the possibilities of a human eye with a human arm. It means we can see and we can do all experiments in situ inside TM under high resolution. And of course, for many years people were trying to get access to nanomaterial properties, and we are not the first to access these properties. But probably people mostly use scanning electron microscopy, scanning tonality microscopy, and atomic force microscopy. All these three techniques are surface techniques, so it means you may get information solely from the surface of your material, not from the bulk. And also in all these methods you need to put your samples on substrates. And of course substrates may affect the properties greatly. But in case of HRTM, which stands for high resolution transmission electron microscopy, we don't need any substrates. We can put materials in a high vacuum in a freestanding shape. And also we equipped with ultra high resolution, spatial resolution, which is 1.7 angstrom in our case. And simultaneously we can get deep insights into the crystal structure, because we have possibilities of electron diffraction, we have possibilities of so-called electron energy loss spectroscopy, so we can get information about specialties of chemistry. And also we are working on freestanding structures. This slide shows you the collection of in situ TM holders, which I was able to gain in last 8 years. I would say that each holder is a rather expensive piece, more than 200,000 American dollars. And that means it took me some time to accommodate all these funds and to get this very sophisticated experimental techniques in our laboratory. All these holders have something in common. On the left side you can see there's a sapphire ball and a gold cap. The gold cap embraced with 6 legs, a sapphire ball, and here is a piezo tube. So this part is piezo driven. And the accuracy of this movement is better than 1 nanometer. So it means you can move this part of the holder with a very high precision. And on the opposite part, on the counterpart of the holder, you can put either STM tip or AFM cantilever. In this case, you can bias the structure and you can analyze current voltage characteristics, so you can get IV curves. If you replace STM tip with AFM cantilever, you can measure the force displacement curves. It gives you information about mechanics. And if you put some bridge inside, so you can get rid of 2 terminal measurements, electrical measurements, which are not very accurate, and you can go to multi-terminal setups with more than 12 different contacts. If you go to 2 independently driven probes and use different tip here, tip material, you can create a thermocouple, very thin micro thermocouple with a tip of only 50 nanometers. So you can trace temperature gradients along the structures. And the final purchase was a so-called optical holder. In this case, we have optical fiber which is protruded into the column, and you can shine the light of any wavelength and any frequency on your structure, which is located on the opposite end. And for all these studies, last year I was awarded with so-called SET award by Japanese Microscopy Society, which is awarded to the best microscopist of Japan in every year, in this case in material science. And that was the first case for foreigners actually. First, my message, I would like to introduce nanomechanical measurements. This may be the most easy to understand section of this presentation, because you can eventually transmit this data at the macro world. So you can think of like normal instrument type machines or Shimazu machines for mechanical tests. First experiment which we designed in 2010, we decided to get idea about what's the mechanical strength, tensile strength of individual single-walled carbon nanotube. I would say that at that time this parameter wasn't known, and that was the idea of this work. But it's very difficult to work with single layer carbon nanotube because it's so thin. It's almost invisible, so it's difficult to clamp it, difficult to see it. And we decided to start with a multi-volt carbon nanotube, which was clamped between tungsten probe and conducting FM cantilever. So what does mean that we can put current into the structure. And you know that when you put current into a conductor, you get so-called Joule heating. You can heat the structure up to very high temperatures. And because carbon has some sublimation at high temperatures in vacuum, if you look carefully at this part of the tube, you can see this is the hottest spot because it's almost in the middle. If you look carefully, you can see that the tube shrinks here. It gets smaller and smaller. So what does mean that we undress the layers one by one, and eventually we end up with just one single graphene layer, carbon nanotube layer, in the center of this tube. And we can evidence that this is real single layer using high resolution imaging. And once we are ready, we can make this single mechanical test on individual single-shelled carbon nanotube, and we get force displacement curve, which can be recalculated into strength, stress, load. And these high-resolution images show you that, in fact, we have single layer of graphite or graphene, or single-shell carbon nanotube in the center, but sometimes the shell can be not very perfect after this undressing, because it's rather hectic technique. And sometimes we have some defects, pentagons or heptagons. These defects are very easily seen by high-resolution imaging. And then you can, for example, you can compare what's the mechanical strength of a perfect tube and what's the mechanical strength of defective tube. And we did so, and we found that if the tube is perfect, if the tube is made only of hexagons, you exactly get 100 gigapascal, as theory predicts. 100 gigapascal, a huge strength, which is, say, 1,000 times stronger than just low carbon steel. 100 times, sorry, not 1,000. And but what happens here? If you have just one single defect on the shell, the strength drops 4 times. You get only 25 gigapascal tensile strength. So it means that every single defect is very important for carbon structures. So be aware that the mechanical strength of carbon materials is very sensitive to point defects. We did the same experiments on boron nitride nanotubes, and sometimes these boron nitride nanotubes, what does it mean? You have alternating boron nitrogen layers, or atoms which substitute for carbon atoms in the lattice, and sometimes they have this funny structures like Japanese bamboo trees. And we started to test this, and I guess you can predict that the fracture will be in the thinnest part between the joints, and exactly it happens here. So the joint is broken, and with the help of some molecular dynamic simulations, we modeled that in fact this process is going in this fashion. and we got the tensile strength of these bamboo-like materials of 8 gigapascal. We continued these runs for ultra-thin silicon nanowires, which we also prepared by ourselves at NIMS. And you can see this is a summary of what had been done. And you can see that we analyzed the silicon nanowires of different diameters, starting from very thin, 8 nanometers, to rather thick, 40 or 50. And the trend is here very clear. The thinner the nanowire, the higher the strength. And the good thing that we can analyze crystal structure, we can be sure that we are dealing with single crystal material oriented along the 1-1-1 direction. And this is just normal stress strain plot. And this movie shows you the real-time fracture, actually speed of 8 times more. It's a fracture of individual silicon nanowire inside a high-resolution electron microscope. And if you look carefully, you can see that almost no plastic deformation occurs here, and the fracture is purely brittle, as molecular dynamic simulations also confirmed. But interestingly, when we change the deformation mode from tensile test to bending, we found that these silicon nanowires, they may have some fraction of plasticity. You can see that the nanowire can be bent, but still the crack is appearing here, and you can see all these dislocation collides, formation or deformation zones, and finally the fracture of this nanowire. And the good thing that this is a low magnification, but at any stage of this experiment, you can zoom in, go to like 2 million times magnification, and you can visualize how the dislocations are moving inside, what's the dislocation core, is there any phase transformation, and what's the chemistry during the deformation, is it changed or not, due to silicon oxide, for example. Very recently, this data is not published. We also address the question of another mechanical task, which is called fracture toughness. There's Young modulus, tensile strength, and another important parameter for mechanical behavior is called fracture toughness. And in this case, what we need to do, we decided to compare graphene versus boron nitride. Boron nitride, that means just boron nitride two-dimensional crystals. And in order to do this test, to compare this test between graphene and boron nitride, and also to be very in the frame of normal fracture toughness experiments, we need to make some notch of different shapes. And because we are armed with an electron beam inside here, this electron beam, if it's focused, we can use it as a cutter, like a razor. And we can make these notches by using this electron beam, and then we can make this fracture toughness test, and we do this test for graphene, for boron nitride, and also we calculated the stress fields by using finite elemental analysis in theory. And what we got, that in respect to fracture toughness, these are graphenes. These experiments, of course, are very delicate and very difficult. So in this case, we were able to test just 3 pieces of each material. But still, we can see the clear trend that graphene is more tougher fracturally with respect to boron nitride, almost twice. And this data we are now submitting for publication. Another inorganic tube, which is very popular and were discovered by Professor Tenner in Israel, they're called tungsten disulfide. We also borrowed these tubes, we borrowed from him. He's my good friend, and we tested for him these tubes. And this individual tensile test on tungsten disulfide. This is multi-layered structures, not single layers. You can see very clearly some peeling, some atomic steps. It's called salt and sheet fracture mechanism. It means external layer is broken, but still the tube survived inside. Okay, I move on to second session of my presentation that was about mechanics, about mechanical properties, what one may get with respect to the numbers. But also microscopy is a very sensitive tool in order to do a lot of non-engineering, very beautiful non-engineering works on a very small objects, which is like down to single-layered graphene and so forth. In this case, we try to make the junctions between different carbon nanotubes. You know, carbon nanotubes are usually rather short, something like 300 nanometers to 30 microns, something like this in regular shape. It means if one wants to use these tubes for some structural applications, we need to find some way how to make connections between different structures and to make the long probes, for example, for space elevator. There's some dream about space elevator. And we found this way. We put two tubes, two multi-layered carbon nanotubes inside TM, and one tube was deliberately filled with cobalt particle. And then we, just by using nano manipulations, we can make this cross inside the microscope because we can manipulate with different structures. And then we put the current into this system, and simultaneously we irradiate the junction spot with the electron beam. And what happens is that instead of two tubes, one is filled, one is empty, in the end we have 4 branches which are clamped with just one cobalt particle in the middle. And here we have covalent bonding between cobalt and carbon. And this junction happened to be rather tough. When we try to dispatch the junction from the tube, it prefers to be dispatched from the electrode rather from the clamp. And we measured this strength of this junction, and it happens to be more than 6 gigapascal. This is rather huge number because it's comparable to the spider silk already. So it means these metals, like iron and cobalt, transition metals, they can serve as very new and very good clamps to make junctions between different structures. And another experiment which I want to show you, it's how tungsten electrode on the right reacts with carbon nanotube. We just connect and then we need to put the current into the system, and you can see that very interesting phenomenon take place. Carbon layers from the inner side of the tube, they start to penetrate into the electrode. It's type of soaking, and in the end you can see that new carbon layers are crystallized on the tungsten tube. This type of, because we have this Joule heating, we have very high temperature in this area, something like more than 1000 centigrades, and we have a lot of diffusive processes. Carbon diffuses into the electrode, and here, if we check the material by electron diffraction, you can see that it's not tungsten anymore, this is tungsten carbide. And once the carbon concentration in tungsten carbide becomes higher than solubility limit, then you have crystallization of new graphitic layers on the formerly pure tungsten tip. The same is true for graphene. When we put individual multi-layer graphene into the microscope, you can see very strong interaction. Tungsten tip eats graphene, and the size of graphene is changed, and resistivity is also changed here. So it means that the message here that these metals like tungsten, iron, cobalt, these electrodes are not good for graphene electronics because there is interaction, diffusive interaction between carbon species and metal species, and you have carbides, and everything is changing with respect to electricity. We also utilized this Joule heating phenomenon in order to analyze what can be the temperature, the highest temperature inside carbon nanotubes when we have this Joule heating phenomenon, and when the tube becomes like electrical interconnector. In order to make this experiment possible, we filled carbon nanotube with zinc sulfide inorganic material with known sublimation temperature. And you can see that if we do biasing of the system, zinc sulfide, this is zinc sulfide filled inside, and in this case, zinc sulfide easily melts inside the tube, and the tube becomes empty. And by knowing the boundary conditions that these electrodes are massive gold parts, so we assume that they are at room temperature, and by knowing that the starting front of the melting is 928 K or 653 centigrades, we can recalculate what's the temperature gradient either along the tube or across the tube. You can see that very big gradients here. The tube walls are rather hot, the center can be still rather cold. So that was the summary of these experiments. Recently, we also find very smart way how to use this Joule heating phenomenon inside TM. In this case, we put single crystals of transition metals like iron or cobalt into multi-volt carbon nanotubes. And again, we just biased the whole thing. And what happens is that during this pulse biasing, the temperature goes up very quickly, up to more than 2000 centigrades. And iron and cobalt immediately melts. At the same time, because we have very intimate contact here between the filling and nanotube, and you know that carbon nanotube is very good thermal conductor, we have immediate cooling of the system. We calculated that heat and cooling cycle can be within just 400-600 picoseconds, very quick heating, very quick quenching. And it means that we achieved record high quenching rates. These quenching rates are not possible in the macro world, but we achieved 10 power of 12 Kelvin per second. And in this case, single crystals of iron and cobalt transformed into amorphous substances. So I would say that these are elemental metals, not carbides. We checked it. These are elemental iron, elemental cobalt. And these materials do not exist in nature. We created amorphous materials inside the nanotubes. And now we can recrystallize this material back, again by using Joule heating. From amorphous phase, we can go to crystalline phase by using the heat of the resistive heating. And I think that's, we called it nanometallurgy approach because it's really interesting to analyze what's the properties of these new amorphous substances. We can do this tensile test, for example, now. So this work is ongoing. And another way of engineering of the structures inside TM, we can use boronitride nanotube, freestanding boronitride, in order to charge this, because boronitride is dielectric, it's insulator, so it doesn't conduct current, but when we put electron beam, we can charge the structure greatly. And in this case, we have this interesting phenomenon, it's called Coulomb explosion. At some point, we have this exploded layers one by one or in some packs, and the tube gets shorter. You can see actually these are boronitride graphene when we just charge the structure by electron beam. And also recently, together with people in the audience, namely Dmitry Kvashin and Pavel Sorokin, and my postdocs in Japan, we performed this very delicate and very interesting experiments. We were trying to model the so-called scotch tape technique, when you try to peel off graphene, you need type of scotch tape. In the microscope, instead of scotch tape, we can use very sharp tungsten tip. You can see the tip range is something like 10 nanometers only. We can chemically etch this tip down to very small diameter tip, and then we use molybdenum disulfide as a model crystal, because molybdenum disulfide quite often has some atomic steps on the surface. These atomic steps we can use as hooks, and we can peel off individual molybdenum disulfide layers from the crystal. In this case, this movie shows you that we can peel off just 2 atomic layers, or next movie shows peeling of 3 atomic layers. And Dmitry and Pavel, they calculated the energetics of this process, and also if the structures are rather big, we can measure the force. And this plot shows you the kink formation, and every kink formation is associated with a drop of force. In this case, it's rather big crystal, but we cannot measure the force for very tiny flakes, because we can measure the force in the range of not less than 3 nanonewtons. But for big crystals, it's possible. And for any crystal, it's possible to calculate this stress-strain distribution over these flakes. And if we peel off just 1 atomic layer of molybdenum disulfide in collaboration with a group of Boris Jakobson at Rice University, we calculated a very important fundamental quantity. This is called surface energy. We calculated surface energy of molybdenum disulfide crystal, which becomes 0.11 Newton per meter. And this slide shows you actually the power and the beauty of the modern electron microscopy. In this case, I used the so-called spherical aberration corrected microscope named Titan Cube, which is also available in our group, NIMS. And we took these flakes, which we peel off, and we put inside TM. We use a double correction system for the monochromator and for the objective lens. And you can see this is just single layer of molybdenum disulfide, and very nice more patterns, and 1, 2, 3, 4, 5 layers. And even you can see the molybdenum vacancies in the structure. And what's most exciting that even light atoms like sulfur, you can still see the contrast coming out of sulfur atoms. They form this type of triangular pattern. We did also recently some experiments on making tungsten disulfide atomic layers. In this case, again with the help of Pavel and Dmitry, we calculated the process in theory by using molecular dynamics simulations. We used tungsten disulfide nanotubes from redshift 10, and by using chemistry, we did this unzipping by tiles. And in the end, we have this very thin tungsten disulfide crystals. It means we just unwrap the tubes. So we can wrap the sheets to make tube, and vice versa, you can unwrap the tube and make sheet. And tungsten disulfide actually is a semiconducting material, but in this process and after unzipping, we have material which has an IV curve, close to metal type of metallic conductivity. If we use this double probe system, so it means in total we have 3 contacts, 2 movable and 1 stable. And if we take graphene nanoribbon, shown here, it has just 3 layers, we can do these interesting experiments. We can use a third probe as a collector of electrons and 2 probes as a drain and source. So once we put the current into the structure, we recorded emission of electrons out of the graphene sheet. So this is also very interesting electron emission from flat surface of graphene. I would emphasize it's not from edges, it's from the flat surface of graphene. And same experiments by using 2 probes. We created these very tiny probes, not made of metals, but in this case they're made of carbon nanotubes. If we put some paraffin drops onto the tungsten tip, then we put some current, and we end up with very tiny probes. And these probes are very robust and they are very elastic. We can bend them as many times as you want without breakage. And the good thing, the tip is only 1 to 2 nanometers thick. It means that by using this simple tester, we can individually measure the electrical resistivity of grain boundaries and grains in ceramics and in metals. And we have these ongoing projects these days in Japan. If we use this type of bridge system, and here the idea was to, you know that very popular process is for making graphene is graphene oxide reduction to make graphene. And we decided to analyze how does it go in real time inside TM. And the strong point of this advantage of this experiment is that we have 3 parameters in one experiment. We can analyze hydrogen imaging, we can analyze chemistry, colors and plasma loss of oxygen and carbon ages, and also at the same time we can measure the electrical current. And what we did, we put graphene oxide sheet on the bridge, and then by using again Joule heating, we just heat the structure, and we found that conductance is increasing 6 times, chemistry is changing, and hydrogen images also changed. And we came up with this conclusion that chemically the process of graphene oxide reduction goes from losing first epoxy groups and then hydroxyl groups. That was the conclusion of this project. Not only individual structures, but as I mentioned in the first slide, we can analyze different nano devices inside TM, make some prototypes, and to see what happens when we, for example, construct a lithium-ion battery inside TM. This is copper oxide nanowire. This nanowire serves as anode, and we put lithium foil and ionic liquid as an electrolyte, and then we just need to charge the whole system to bias, and then you can see how actually the lithium penetrates into the anode. The structure changes. You can see some type of crystal amorphous transition. And what's good that at every stage of this process, we can stop, we can analyze the chemistry, and we can get an idea what material is good, what material is bad for serving as anode of lithium-ion batteries, because for this type of devices, reversible cycles are important. If something is irreversible, like phase transformation or chemical transformation, material is not good anymore. Okay, last topic is related to the final holder which I showed, and the idea was to try to merge all possibilities of TM in one instrument. high resolution, nanomanipulation, which I discussed, and also power of light. And we designed this holder. You can see this white light coming out of the tip of the holder. And in order to make these experiments possible, we also implemented specially designed tungsten probe manipulator. Here's optical fiber, there's a specimen here, and nanomanipulator. It means that the light of different intensities, different frequencies, different wavelengths go inside TM, and now you are armed with very new technique to analyze photocurrents, photovoltages, and what's important, under the strain. This is very important for flexible electronics, for example. And of course, we need to spend a lot of time for tuning the system because we are working on individual nanostructures. They are just 20 nanometers, 50 nanometers wide, so it means the signal is rather weak. We need to use local amplifier to enhance the signal to noise ratio, but we did so, and also we use all these optical tricks like monochromator, chopper, and different Kissley devices. And this is just a very simple experiment to convince you that it's possible. We have individual nanowire of this composition. Inside TM, light comes from this way, and then this is a dark current when the light is switched off, and this is a photocurrent when the light is on. At the same time, we can analyze diffraction patterns. We know the defects, we know the crystal structure of the material, and because my time is running out, I just want to show you as small cartoons of all experiments which are possible. For example, titanium oxide, very popular material for photocatalysis, but in this case we can choose the crystal phase of titanium oxide nanoparticles. We can selectively analyze a photocurrent and photovoltage from different phases of the material, and we can get some recommendations for the industry which single crystals of titanium oxide nanoparticles are good and they have better optical performance. Same experiments are possible for cadmium nanobelts. You know, cadmium sulfide is a very important material for flexible electronics, and this experiment we designed to analyze how the performance degrades when we bend the structure. It really degrades. You can see photocurrent drops from 0.73 to 0.54 after the bending inside TM. Molybdenum disulfide nanosheets were also studied recently. We get very clear photo response, and at the same time we analyze atomic resolution and crystal structures, different heterostructures. In this case, again, we prepared this structure by ourselves, and we can compare how the single material, cadmium sulfide, is worse compared to heterostructure, which is made of two, zinc oxide and cadmium sulfide. Both are very popular optical materials. Both have some advantages and disadvantages. Once you merge them in one structure, the material performs much better. You can see on-off ratio increases dramatically for heterostructures. And at the same time, I repeat it many times, you can see all information about your material in situ. You can see zinc oxide branches, cadmium sulfide cores, and diffraction patterns, chemistry, whatever you want. And the last example, not only very primitive experiments on photocurrent and photovoltage, but sometimes you can get a lot of information about electronic structures. In this case, we deformed zinc oxide nanowire, and we did this photocurrent spectroscopy, and what we found, once we bend the structure, there is a splitting of two peaks in the central part. And if you look carefully, one part, when you bend the structure, one part becomes compressed, one part becomes tense. And according to theory, compression and tension gives different effect on the bend structure of the material. And what we actually observed this for the first time, maybe I would say it's optomechano-electrical coupling. This is the first experiment on merging all these three techniques in one set. And because we prepared all these materials at NIMS, I think I have enough time until my retirement to analyze all optical properties of these inorganic materials. And my summary tells you that the information in regards of diverse material properties is only possible using this in situ TM at this level of spatial and temporal resolution. And actually I wanted to introduce some mega grant activities which I'm involved in, but I think time is not enough, and I just go to the summary. And these are highlights in the literature over the last 10 years of my group, and thank you so much for your attention.